Hey everybody, here's our review for our second CBA. Make sure you start by putting your name. Make sure you put your name so you can get those extra points on your test grade. Okay, so our first question here is about stoichiometry. Remember, stoichiometry was like essentially grams to moles to grams, right? It says list the 4 mole conversion factors. Well, you can cheat a little bit. 3 of them are right here. So the first one is 1 mole is equal to 6.02 times 10 to the 23rd. And we can shorten that to particles, right? But that's this one. And particles is, remember, formula units, molecules, atoms, ions, anything like that. And so I'm not going to write these other two. This one is the second one, and this one is the third one. Write those down. But what's the last one? Well, the last one is our mole ratio. So we're saying moles of given equals moles of unknown. And the reason I put that little dash in the front is because we don't know the numbers until we see a chemical equation. Because our mole ratio, in our mole ratio, the numbers always come from a balanced chemical equation. So make sure you write all those down to get full credit. And let's move on to the first part here. So remember way back when we were doing all this, we had our given, our unknown. If there's molar mass, we put it here. So here it says, if you started with 4.00 moles of sulfur dioxide, how many molecules would you have? So this is just about the mole. What's been given to us here is 4.00 moles. And what is our unknown? How many molecules? So our unknown is molecules, and you can use whatever abbreviation you want for molecules as long as you understand it's right here. It's molecules, right? So we're going to do step 1, step 2, step 3. Step 1, we're going to rewrite our given. Step 2, we're going to multiply by a fraction. Step 3, we're going to put our given unit on the bottom of our fraction. Okay, now let's look. This is moles to molecules. If I have an equation with moles and molecules, I can just do one fraction and I'll be good. And I do have an equation, moles and molecules, so I can just do one fraction. So I'll do molecules on top, and I'll be done. Now I just need to match my numbers. Remember, the numbers in our fractions always come from an equation of some sort. They never come from over here. We already used that number. We're done with that number. The numbers have to come from one of these. So this one says 1 mole, and molecules is 6.02 times 10 to the 23rd. Let's put that in our calculator and get an answer. Okay, so we're going to do 4.00 times, and then remember, we're going to make a fraction by doing alpha y equals enter. Make our fraction. And then on the top, we're going to do 6.02. And then I think you should do the E. We're going to do second, comma, gives you the E. Remember, E, 23. No need to hit the caret button, right? We don't have to hit that button. We just do E23 on top. And then on the bottom, we put a 1. We hit enter. We're going to get our answer. Our answer is 2.4. But then don't forget, look, you got to look all the way to the end. It says E24. Now, I don't care about the numbers in the middle, but I care about the first 2 or 3 numbers, and I care about that E24. Without that E24, this is incorrect. So it's 2.4. E means times 10 raised to the, and then 24. And there's our answer on that one. I know it's been a while since we've done this, but you will have these numbers. You will have all of these supports for you when you take your test. Okay. Just remember step 1, step 2, step 3. Write your given, multiply by a fraction. Given unit goes on the bottom of your fraction. All right, right here it says, in the formation of water, hydrogen gas reacts with oxygen gas to form water. If you start with 7.545 moles of hydrogen, how many moles of oxygen do you need? So this is a stoichiometry problem where we're going to use our stoichiometry map. Let's write our given. They've given us 7.45, 7.45. And then when we're doing stoichiometry with this big map here, we have to put our substance, right? So we got 7.45 moles of H2. And then it says our unknown, how many moles of oxygen? We need both of those things. And don't forget, this is oxygen here, O2. So our unknown is moles of oxygen. They didn't give us any molar mass, so we're not going to worry about that right now. Now, a quick refresher on how our mole map works. Our given is always where we start, and our unknown is always where we end, right? Here's given, here's given. That's where we start. So we got to start on one of these two on the left side. This one says given grams. Is our given in grams? No, it's not. So we're not going to start here. Here it is, given moles, given moles. So this is where I'm going to start. And then over here, my unknown. So unknown moles or unknown grams. Well, it says unknown is moles. So this is where I'm going to end. So I don't need to do this step, and I don't need to do this step. I only need to do the mole ratio. So again, as I always do, I'm going to rewrite my given. I'm going to multiply by a fraction. This time my mole map is going to tell me what goes in my fraction. So my stoichiometry map, my stoic map tells me my moles of unknown go on the top. So I'm going to put moles of O2, and my moles of given go on the bottom. So I'm going to put moles of H2. Remember, when we do the mole map here, we're only talking about the substance. We don't care about these numbers. We already use that number, right? Because anytime we write a fraction, this number comes from some equation. And guess what? Here is our equation, the balanced chemical equation. So anywhere I see H2, I'm going to put the number 2. And anywhere I see O2, I'm going to put the number, there's a 1 right there. I know there's no 1 written there, but if there's nothing, that means it's a 1. Okay, so again, don't forget, anytime we're using our mole ratio, we're going to get our numbers from the balanced chemical equation. Okay, so I had said that, how do we do this one? So I had said, that we are going to start here and end here. And so this is the only step we have to do. This is the only fraction we have to do. Let's multiply that out on our calculator. So I'm going to do 7.45 times. I'm going to make a fraction. Green button, y equals enter. And I'm going to put 1 on top and 2 on the bottom, just like my fraction says. And I'm going to get 3.725. And this is going to be moles of O2. Whatever I end up with at the top and the end, that is what I get. Now, if we look in our calculator, there's no E, so that's our full answer, 3.725. That's it. All right, now that we're kind of getting the gist of things, I'm going to move along a little bit faster with some of these, all right? When aluminum reacts with sulfur, it forms aluminum sulfide. If you start with 7.57 moles of aluminum, what mass of aluminum sulfide would you need? Again, we have our stoic map. Let's write our given. 7.57 moles. And this time we're talking about aluminum. Remember, our given is the number and the unit and the substance that they give us in the problem. And then let's see. If you start with that many, it says what mass. What is mass? Mass is grams. That's my unknown. What grams of aluminum sulfide? Now, if you didn't know what aluminum sulfide was, you could just go ahead and look over here at your equation. Like, that's clearly aluminum. That's clearly sulfur. That's got to be aluminum sulfide. And then it says our molar mass for aluminum sulfide, Al2S3, is 150 grams. So we're going to put that above here. And remember, if we put something in here, it's going to go in our first fraction. And if we put something in here, it's going to go in our second fraction or our last fraction. So we're going to make sure that that number 150 is in our last fraction. All right, let's look. Where do we start and where do we end? We always start on the left side. Where's our given? Our given is in moles. So we're going to start right here. That means we don't do this step. And then our unknown is in grams. That says unknown moles. That says unknown grams. So here we're going to end here. Oh, it's a dreaded two-step problem. Two-step problems are the hardest ones because you have to figure out where to start and where to end. But we have our map. So let's rewrite our given. Let's multiply by our first fraction. Our first fraction is our mole ratio. It says moles of unknown on top. So we're going to put moles of Al2S3 on top and moles of given on bottom. My given is aluminum, moles of aluminum. Cool. Now up here, Al2S3 is right here, aluminum sulfide. There's no number in front of it. That means it's a 1. That number goes here because this is our mole ratio. And then aluminum is right here, a 2. So we put a 2 right here. That's our first fraction. All right, we made this step. Now we got to end over here. We got to make this step now. So now we got to do this fraction. This fraction says multiply by, and it says on the bottom, it literally says 1 mole. Now I've seen people try to put another number here. If it tells you 1 mole, you just put 1 mole. Good job. 1 mole of unknown, which is Al2S3. And then on the top it says grams molar mass. Remember, we said we were going to use this number in our last fraction, and that's exactly what we're going to do. That's the molar mass, 150 grams. Let's calculate that out. Okay, so we're going to do 7.57 times, make myself a fraction, 1 over 2 times, make myself another fraction, 150 over 1. My answer here is 567.75. There's no E, so we're good to move on. All right, number 5. Ooh, this one's a little more complicated, but I think we'll be all right. It says sodium and fluorine react in a synthesis reaction to produce sodium fluoride. In a particular experiment, an 11.15 gram sample of fluorine reacts completely. The mass of sodium needed is blank grams, and then it gives us 2 molar masses. All right, this looks like a long one. Let's look at our given and our unknown. Our given is always the number and the unit and the substance that they give us. There's our given, 11.15 grams of F2. In our unknown, it says the mass of sodium needed is blank grams. So we need mass of sodium. So the grams of sodium is our unknown. And then it gives us 2 molar masses right here. Molar mass of F2 is 40 grams per mole. And the molar mass of, that should say sodium. A little mistake there. No big deal. And I'm going to look up the molar mass of sodium just to make sure real quick. Okay, yeah, that is the correct molar mass of sodium. It's supposed to say molar mass right here, so let's pretend it does. And that's 23 grams. All right, just wanted to make sure. Okay, so let's do this. So if our given is grams, we're going to start here. And if our unknown is also in grams, then we're going to end over here. We always start at our given and end our unknown. So we're doing all 3 steps. We also said that this this number right here is always going to go in my first fraction, and this number right here is always going to go in my last fraction, my third fraction. All right, let's start it up. We're going to rewrite our given. I'm going to run out of room here. I'm sorry. 11.15 grams of F2. Then we're going to multiply by our first fraction. Our first fraction literally says 1 mole on top. So I'm going to do that. 1 mole of F2 on top. And on the bottom, we said we were going to use this in our first fraction. So that's going to be 40 grams of F2. All right, good job, us. We use this one. We use this one. We're done with those numbers. All right, that was our first step. We took our first step. Let's take our second step. That's this equation right here, the mole ratio. The mole ratio says, let's put our moles of unknown on top. My moles of unknown are, I know this says grams, but we're talking about the substance, moles of sodium. So that's what we're going to put. Moles of sodium goes on top. And then on the bottom, it says moles of given. Again, I know this says grams, but we're going to use moles of F2 because we're just following our fractions here. Okay, anytime we have moles over moles, anytime we use the mole ratio, we got to get our numbers from the balanced chemical equation. This is the only time we use these numbers, right? So I'm going to find sodium, Na, it's right there. It's got a 2 in the front, so I'm going to put that right here. And I'm going to find fluorine, that's F2. It's got nothing in front, that means it's a 1, right? Let's put a 1 down there. All right, we took our second step. Good job, us. We're not done. We still got to get to this last step. So here's our last fraction. All right, and we said we were going to use this one in our last fraction, and here we are, grams on top, the molar mass of sodium on top, 23 grams, and 1 mole at the bottom. Again, if it says 1 mole, you go ahead and just put 1 mole. All right, we use that up. Let's put this into our calculator. 11.15 times a fraction. My first fraction is 1 over 40 grams times another fraction. This fraction is 2 over 1 times my final fraction. And my final fraction over here is 23 over 1. We hit enter, we're going to get 12.8225. We can round that a little bit. 12.8. And this is grams of sodium because that's what our unknown is. That's what we're looking for. All right. Next problem. All right, in the reaction with iron in the presence of oxygen, iron oxide is formed. If you have 84.7 grams of iron, how many moles of oxygen do you need? And then it gives the molar mass of iron. Iron is Fe. All right, hey, let's keep it straightforward. We don't have to worry too much about what all these things are. We're just going to look for our given. Our given is always the number that's in the problem. This is the molar mass. This is not part of our given, okay? But here it is, 84.7. So my given is 84.7. What unit? Grams. What substance? Iron. If you didn't know, iron was Fe on our periodic table. What's our unknown? How many moles? My unknown is moles. What substance? Moles of oxygen. Oxygen is always going to be O2 in your balanced chemical equation. And then it gives me the molar mass of iron. Iron's over here, so I'm going to put that molar mass above iron, 56 grams. And we know that this is going to go in our first fraction. So let's write this all out. We're going to write our given. Ooh, I've gotten ahead of myself. Well, it's okay. 84.7 grams of iron. It's okay, I'll go back. Okay, where are we starting? Where are we ending? That's more important. Let's look at our stoic map. So it says we're going to start on given grams. So here's where we start. And we're going to end on unknown moles. Right here, unknown moles. So we're not going to do this last fraction. Right? We don't need to do that. Another dreaded two-step problem. These are the hardest ones. Okay, so we're going to multiply by a fraction. Our first fraction is going to be this one. And we said we're going to write 1 mole over, and we said this was going to go in our first fraction, 56 grams, the molar mass of iron. Cool. We made our first step. Now we need to make our second step. We're going to use now the mole ratio. Multiply by a fraction. What goes on the bottom of my fraction? It says moles of given, so moles of iron. And on top it says moles of unknown, so moles of O2. Again, I know that this says grams, but when it says moles of given, you're just going to use your substance, okay? All right, we've written this down, we've used all that. We just need to put this last part in. Let's go to our balanced chemical equation. That's where we get these numbers from. O2 has a 3 in front, so that's what we're going to put here. And Fe has a 4 in front, so that's what we're going to put here. And we calculate it out. $84.7 times, let's make ourselves a fraction, 1 over 56 grams times, let's make ourselves another fraction, 3 over 4. We hit enter and there's our answer, 1.13. Whoops. 1.13 moles of O2. All right, good job, us. We're halfway done. Okay, I don't want this video to be an hour and a half long, and you gotta work for something for this extra credit. So number 5 and number 6, it's more of the same thing. Go ahead and work through these two on your own, and make sure you get them done so you can get the full credit for that, the extra points. All right, here we are in gas laws. So we're getting through everything. This is what we did right before we left for spring break, remember? So here it's asking about relationships. Remember, our main equation is PV over NT. P times V over N times T. Excuse me. And we said we can use this equation here, or really it's just a fraction, it's an expression. We can use this equation here to figure out all the different relationships. We said if they're on a seesaw, then when one goes up, the other goes down. Or if they're in an elevator together, like volume and temperature, then when one goes up, the other goes up. Or if one goes down, the other goes down. I don't want to put both of those, that'll confuse us. They change the same way. So they're either on a seesaw or they're in an elevator. So let's look at these things. Oh yeah, we called this an inverse relationship, and we called this a direct relationship. Over here, pressure and volume. So if I got pressure and volume are next to each other. Pressure and volume are on a seesaw. So these have an inverse relationship. Opposites, they change opposite. Temperature and volume. Look at that. They're on an elevator together like this. So they have a direct relationship. Moles and volume. Now I know moles and volume are like across from each other, but if I rewrote this equation with just moles and volume, it would be volume over moles just like that. If I took out these other two, and that is an elevator. This is a direct relationship. Pressure and temperature. Same thing with pressure and temperature. I know they're across from each other, but if we rewrote this without the other two things, pressure and temperature are on an elevator, another direct relationship. Pretty straightforward. I want us to think about this. I want to say this without giving away too much. I wanted us to think about this too in terms of like, if I had two different things, let's say, oh, let me get that one back. Um, like for instance, if I had three closed bottles, and this one had 2 moles of gas, and this one had 3 moles of gas, and this one had 4 moles of gas. So we're talking about N, right? Which one of these would have the highest pressure? So if the relationship between moles and pressure is a direct relationship, right? If one goes up, the other goes up, then we could say that this one, because it has the least amount of moles, also has the least amount of moles, it also has the lowest pressure. And this one has the most amount of moles, so this one also has the highest pressure. And this one's in the middle because it's got the middle amount of moles. I also want us to be able to do that with these relationships here. Just make sure we can figure that out. Cool, cool, cool. Some problems. Remember, we've got these two equations. This one has 1 and 2, 1 and 2, 1 and 2, because this is the one we use when things are changing. And this one has 1 of everything because this is one we use when things are not changing, right? No pressure change, no volume change. So let's read our question. It says, you have a piston whose initial pressure is 851 millimeters of mercury in a container that is 0.53 liters. If the piston moves, ooh, that's a change. Something changed, so we're going to use this one. If the piston moves to a new volume of 4.5 liters, what is the final pressure? Okay, so don't forget, if it's got a weird unit, mmHg, what's that? I don't know, then it's pressure. It's always pressure, okay? So that's going to be our first pressure, 851 millimeters of mercury in a container that is 0.53 liters. That's definitely volume, 0.53 liters. Cool. And it says the piston moves and we have a new volume of 4.5 liters. What is the new pressure? We don't know our second pressure. Now, this particular one, it really trips up a lot of people because most of the time when we do this equation, we'll end up with a fraction of some sort, but not this time, right? Don't forget, if I'm not using these, I'm going to cross them out. So let me cross them out here too. And if we do that, we do not end up with a fraction. We end up with P1 times V1 equals P2, equals P2 times V2. No fraction for when we have pressure and volume only, okay? So let's write these out. Pressure 1 is 851. Whoops. How did I do that? Oops. Oop, that's a new thing. Cool. Okay, so pressure 1 is 851 millimeters of mercury. I'm going to leave the units out for just now. Times volume 1, which is 0.53 liters, is equal to pressure 2, which we don't know what that is, times volume 2, which is 4.5 liters on that one. Okay, and then here we just do some basic algebra, right? We need to get x by itself because that's what we're solving for. So if we do right here to get x by itself, we're going to do the opposite of whatever this says. So this is x times 4.5. So instead of multiplying, we're going to divide by 4.5. And that cancels out on this side. What you do to one side, you must do to the other. So now we get x equals 851 times 0.053 over 4.5. Let's calculate this out. I'm going to make this easy. I'm just going to put that fraction right into my calculator. Whoa. So we're just going to do 851. Nope. We're going to make a fraction first. Oops. We're going to do 851 times 0.53 over 4.5. We're going to hit enter and we're going to get our answer of 100. What a nice round answer. So our pressure 2 is equal to 100.2. We can round to 100. It says, what is the pressure in a container that has 8.45 moles of oxygen at 300 degrees Celsius in a container that was 6.15 liters? All right. So on this one, automatically, we got to get rid of this. We never use Celsius. If you see Celsius, you automatically change it. So we said we need to change it to Kelvin. So we're going to do 300 degrees Celsius. To change to Kelvin, you always add 273. I'll go ahead and do that calculation for us. So instead of 300, we're going to have 573 Kelvin, and that is our temperature. Okay, it says, what is the pressure in a container that has 8.45 moles? That's my moles right here, 8.45 moles, and is number of moles. At a temperature of 573, that's still my first temperature. That was 6.15 liters. That's volume. And that's the whole question. So notice I didn't have a second volume or a second temperature or a second number of moles. So we're not using this. We're using the ideal gas law when things are not changing, nothing changed. And of course, we're solving for pressure. All right, there are two ways to solve for this. Some people like to say, okay, if I'm solving for pressure, then I need to get pressure by itself. So I would do pressure is equal to nRT over V. Now, most people don't like to do that, so I'm going to do it the other way too. All right, let's fill in this equation. My pressure is X, I don't know what my pressure is, times V, 6.15, is equal to N, which is 8.45, times R. Don't forget, R is the universal gas constant. We'll give you this number on the test, 0.0821, times my temperature, which we calculated to be 573 Kelvin. Excellent. So there's a couple of ways we can go about this. I feel like the way that people liked most was first, we're going to multiply these three numbers. We're going to combine like terms, and we're going to get an answer. Let's do that in our calculator. Whoops. Let's bring our calculator up right here. So we're doing the right side first. We're going to do 8.45 times 0.0821 times 573. That's going to give me a nice number. This is going to turn into 397 point, we can round it to 0.5, right? And I'm going to bring these numbers down. So x times 6.15 equals 397.15. Okay, now this has become pretty simple. We just need to get x by itself. What we do to get x by itself is the opposite of what this says. So this is x times 6.15. So we're going to do x divided by 6.15. Cross that out. What we do to one side, we must do to the other. 6.15. Let's put that into our calculator. 397.5 divided by 6.15 equals, and that's going to give us 64.6. Pressure is atmospheres. All right, and finally, it's what we learned just the last time that I saw you. Write the formula for molarity, write the formula for dilution. Molarity, don't forget, molarity is big M, and big M is equal to moles of solute over, please don't forget this, liters of solution, not anything else. And dilution calculation is the concentration times the volume. is equal to the second concentration times the second volume. And those are both right here. Remember, we're going to use our molarity wheel to figure out molarity. Not too much left, 3 more. Okay, the first one says, what is the molarity of 0.5 liters of solution in which you added 0.25 moles of sodium chloride? So in this one here, we set our key to, like, am I using this one or am I using this one? Our key was how many numbers did they give us? This one gave us only 2 numbers, liters and moles. That means we're going to use this one because we got 2 and we solve for the third. If we got 3 numbers, we use this one and solve for the fourth. Okay, so it says, what is the molarity? Don't forget, molarity is big M, and that's my unknown. That's what I'm looking for. So we said, whatever our unknown is, we cross it out of our molarity wheel, and then we do what this says. This says moles over liters. So I'm going to take 0.25 moles over 0.5 liters equals, let's put that into our calculator. So we can make a fraction. 0.25 moles over 0.5 liters. You could also just, 0.25 divided by 0.5 is the same thing. We're going to get the same answer over here. Our answer is 0.5. We were looking for big M, so molar. All right, this one says, what volume of 2.5 molar sodium hydroxide must be used to make 30 liters of a 0.5 molar solution? Again, there's one of our key things that we were looking at. This tells us something. So look, we got 1, 2, 3 numbers. We said if we got 3 numbers, we're going to use, we're going to use this equation here. And if we're using this equation, we can use our little trick. 2 numbers will always go together. These 2 numbers go together. And this number is by itself. This is our bat. This is our ball. So we multiply the bat. We're going to say 3.0 times 0.50 divided by, we can make a little fraction, the other number, 2.5. I'm going to allow you to put that in your calculator and figure it out on your own. All right. All right. Next one. Last one. Make sure you put the answer. You need to get your full credit. All right. It says, what volume of a saturated 18 molar sulfuric acid solution is needed to make 0.009 liters of a 9 molar solution? Okay. Well, this one again has 3 numbers. And these two very clearly go together. So we're going to do the same thing. Multiply the bat, divide by the ball. 0.009 liters times 9 molarity divided by 18 molarity. You put that in your calculator and you're going to get a good answer. All right, make sure you do all of that. I need to see answers here to give you credit. Okay, there's one more thing I wanted to add to this part. Don't forget, if we're doing this one, this one has to be in liters. It must. So if you get milliliters, like let's say you got, 931 milliliters, you need to divide by 1,000 to get liters. This one doesn't matter. This one could be milliliters or liters. It doesn't matter as long as you keep it the same on both sides. But this one has to be in liters. So if you get milliliters, make sure you divide by 1,000. Cool. That's it. Let me know if you have any questions.